So today's lesson is going to be about work. So we all have our own definitions about work. We could say we're going to work out. We could say we're going to mow the lawn. We could say we're going to ride our bike. What else is work? Even right now, maybe writing with your pen you consider work. In all things with work, there's two things you need. You need a force, you need a distance. And so we're just going to define work as being a force applied over a distance. So the equation is pretty straightforward. I mean, if you think mowing the lawn, if you have to push a bigger lawnmower, there's going to be a greater force and you're going to do more work. If you mow a bigger lawn, there's going to be a greater distance. You're going to also do more work. The units we use, well, units for force are newtons, unit for distance are meters. This gets renamed as the joule. And one of the key components you have to think about is we want our force and distance to be parallel to each other. So oftentimes I'll write this equation not force times distance, but force parallel to distance. So we'll see how these play out in some examples we're going to do. So let's do a real simple example. Let's imagine we're going to push an object horizontally. So for example, here I am, I'm going to push, let's say, a 2 kilogram object with a 10 Newton force over a distance of 5 meters. So the amount of work I do is going to be, well, simply force parallel distance. So my force is 10 newtons, my distance is 5 meters, they're both parallel to each other, so the amount of work I do, 50 joules. What about this? What if we pull an object at an angle? So let's say this time I'm pulling with 10 newtons, let's say it's 60 degrees. 2 kilogram object, and we'll pull the same 5 meters. Okay, so remember, since work is force parallel to distance, since my force is not parallel, what I have to do is find the component of force that is parallel. So we want to find this piece of force that's horizontal. So for this, we'll simply do 10 cosine of 60 degrees. So that would be our force that's parallel to our distance. Here is again going to be 5 meters. Okay, so that's 10 cos 60, which is 5 times 5 is 25 joules. So notice that when I pull at an angle here, I'm actually doing less work. What about if we lift an object? So imagine I'm going to lift up my 2 kilogram box. We'll say a distance of up over my head 2 meters. And again, we want to know the work. So notice here, the box itself has a force. If we did our FBD on the box, we'd have our force of mg pulling down. And I'm going to lift up with my applied force going up. So notice, in order for me to lift this weight, I would have to apply the same force as the weight. I'm literally lifting a weight here, right? So this would be, my applied force would have to be the same as the weight. So we'll say FA is equal to mg here. And the distance would be 2 meters. So when we do our work, which would be force applied times our distance, notice that our force and our distance are parallel. Don't have to mess with that. So this would be the mass of 2 times 9.8 times 2 meters gives us 4 times 9.8, that's 39.2 joules. Okay, next one, let's say we're going to carry an object horizontally. So here we are, we'll take our 2 kilogram mass and we're going to carry it this way. We'll say 5 meters. Okay. Think about this one first. Why don't you push pause and think about the answer to this. Okay, you back? In this problem, notice our force is up. So we're lifting this up. We have to overcome weight. We're just holding it here, but we're going to be lifting it up this way. However, our distance is in this direction. So remember, work is force parallel to distance, but since our force is up and our distance is horizontal, these are perpendicular to each other. So there is no component of force that is parallel to this. So in this case, the amount of work we do is actually simply going to be 0. So you want to watch out for this. Whenever our force is perpendicular to our distance, we're actually doing 0 work here. We're just holding this up. We're not moving it any distance horizontally. Any distance vertically. What about this? Let's carry an object up some stairs. Take our 2 kilogram object. Let's go up some stairs. Okay, let's say this distance is 4 meters. Let's say this distance is 3 meters. Therefore, this we'll just say is simply 5 meters all the way up. Again, why don't you take a moment to see if you can solve this one on your own. Alright, back. So this one, again, our force, we're lifting this straight up. So our force applied is going to be straight up here. And our distance, well, I gave you 3 distances. And remember, since work is force parallel to distance, we want to find the distance that is parallel to the force. So earlier we changed our force to make it parallel to the distance. In this one, what we're going to do is we're going to make our distance parallel to the force. So we're going to use the 3 meters as our distance here. So again, remember our F applied has to be equal to our weight here. So this would just be mg times our distance up, which is going to be 2 times 9.8 times 3. Okay, so that's what, 6 times 9.8, that's 58.8. Hope that's right. You can check that for me. Alright, so that's how much work we're doing lifting it upwards, up the stairs. What about friction? What happens if we put some friction in the mix? So for example, let's do that very first one that we did when we were pushing with 10 newtons for 5 meters. Let's say this time though there's 3 newtons of friction. How does that change it? Well, the answer really is, what are you looking for? Who's doing the work? So for example, if it's the work of me, well, that's just my applied force again, which would be 10 newtons times 5 meters, 50 joules. Notice that that is exactly the same as the one we did before. But maybe I'm going to ask you for the work done by friction. Well, friction's doing work as well. Notice that the force of friction is to the left, and the distance we're moving is to the right. So when we do our force here, we're going to actually use negative 3 newtons times 5 meters, which would be negative 15 joules of work. So friction, you can see, is it's kind of opposing. It's taking away some of the work that we might be doing. And if you take a look, let's look at our net work. This would be the overall when you look at both of them. Well, you can clearly see 10 and 3, the net force would be 7 newtons times 5 meters, which is 35. And you can check out how this works, because if this is 50 joules, negative 15 joules, notice that that's going to add up to a total of 35 joules. Alright, so those are various examples of work. We're going to get into energy, the concept of energy, and I know you guys have talked about this a lot over your science careers, but basically energy, we say something has energy if it has the ability to do work. So if something can do work, has the ability to, then we say that it contains energy. And we'll talk about the various energy forms, but that's kind of our basic definition of energy. Then probably the most fundamental law of physics is the conservation of energy. And I'm sure you've heard of this before. Energy cannot be created or destroyed. We can only change it into different forms. So that's going to be a big concept in this unit, where we're going to be changing our energy into various forms. Let's go over some of the basic forms that we have. There's 7 basic forms. Mechanical energy is essentially energy in motion, of like kind of large scale motion, so cars, planes, swimming, moving, any kind of moving, motion. Okay, chemical energy, this would be kind of energy contained within chemical bonds. So examples of this might be food, for example. That's where we get all of our energy, is from the food that we eat. Gasoline, etc. Wood, when you burn wood, before you burn wood, it starts with some chemical energy, and then after you burn wood, where it get with the thermal energy or heat energy, right? Radiant would just be light energy, or all the invisible forms of this, ultraviolet, radio waves, etc. Sound would be, well, the energy right now as I'm talking. This would be our sound energy. Electrical energy would be the energy of electrons, and you're watching this through YouTube, and that's utilizing the energy of electrons. And then nuclear energy would be energy contained within the nucleus. So nuclear bombs, for example, use this. The sun is a huge source of nuclear energy. So again, we're going to talk about conservation of energy going forward. It's just a good idea that you have a feel for kind of these various energy forms. All right, let me know if you have any questions.